Thank you, Doctor. And good afternoon, ladies and gentlemen. I hope you are not sleepy now after lunch. And my name is Yitao, and today I'm going to talk about seismic impedance inversion using deep learning. So here we use talk about two methods in deep learning: physics-driven and data-driven methods. So first introduction. So for seismic impedance, it can be used to indicate rock properties like lithology and porosity and fluid types. So in deep learning, there are two major methods to do this job. The first one is physics-driven method. You can also call it model-driven. And the second one is data-driven methods. For the first one, physics-driven methods, it's incorporating physics laws to constrain the learning progress. So it can be supervised learning, and it can also be unsupervised learning. It depends on do you provide any labels to do the job. And for the second one, data-driven methods, it is building a nonlinear and complex mapping between seismic data and impedance log. So which means it needs a lot of labels to do this job. So which means it's supervised learning. And for the objectives of this research, first, we want to observe the difference between these two methods in seismic impedance inversion. And second, we want to achieve a good result of seismic impedance inversion using deep learning with just a few number of well loggings. So second part method. So here's the picture show the working flow of physics-driven method. So for first one, we input seismic data to our model, deep learning model. Here we use a UNet model. Here we can see this encoder and decoder network. And then we will get the predict impedance here. Then we will calculate the reflectivity based on the predict impedance, and then convolve it with a wavelet and generate a synthetic trace. So we will then calculate the loss between the synthetic data and real seismic, and minimize the difference there and get the final well-trained model. And here's some equations we do the job. We calculate the reflectivity based on the predict impedance and convolve it with the wavelet to get the synthetic data here. And for the loss function, which is very important in deep learning, for the physics-driven method, there are two parts of the loss function. The first one, we want to minimize the seismic data and synthetic data here. And the second one, if we have well loggings, we will try to minimize the predict impedance and the impedance calculate using well logs here. And the alpha is a weighting scalar that balances the difference between the impedance log and the seismic data. And here is the second one, the data-driven method here. This is the working flow for that. We can see basically the same. Input the seismic data to the deep learning network and get the predict impedance here. The only difference is that we stop here and calculate the loss between the predict impedance and the real impedance that calculated from well loggings. Here's the equation that we can see there's no involvement of any seismic data or synthetic data here. So one problem that because in reality, we don't have so many well loggings. So we need to generate that loggings, we call it pseudo well logs here. So we use this method that's published in 2022. So here's the input of some well loggings. We'll do the geostatistical simulation here and get a 2D elastic model. And then we'll do the elastic distortion here to generate more realizations of this 2D model. And then it's come to the extent labels. We'll use this as training labels. And here's one application. We applied these two methods on a synthetic model, which is generated by Dr. Zheng in 1996. So this model is here. We can see it contains 14 sandstone with low impedance here, and 15 shell units with high impedance. And here's the corresponding seismic data. And we test in 5 different scenarios with different number of wells. The first one we test both on these two methods on just one well, and 3 wells, 5 wells, 10 wells, 20 wells on just this one vertical section. We can see for this one vertical section, which just contain 512 traces. So those wells just evenly separate along the line. And here's the location of different trees. And here's the parameters of our training. We use the neural network, which has 8 number of layers, both in encoder and decoder. And we treat this problem as a 1D problem. So we predict and train the data trace by trace. So the kernel size is 3 plus 1. And the batch size is 16. And the number of filters here, and we finish the job with 50 epoch. And here we can see that it's the seismic data input. This is the true impedance from the model. This is the one we want to get from the the input. And yeah, one thing I need to mention that you can see from data, this is noise-free seismic data. So because it's synthetic data, so there's no noise in the seismic data. And here's the result of 2 different methods with only one well, just in the middle with only one well. We can see data-driven method has a terrible result because one well is not enough. Even we generate more pseudo wells, the one well is not enough to get a good result here. But we can see physics-driven because we majorly rely on the difference between seismic data and the synthetic data. So the result is good. And if we increase the number to 3, we can see the result using data-driven becomes better. But still, it's not the horizontal layer for the same sand horizon here is not continuous. So, but you can see the phase-driven is still good. And when we increase to 5, the data-driven method becomes better than before. And here's the 10, it's much better than before. And finally, with 20 wells in just for this one line, which has 512 traces, the data-driven method get a good enough result. But the physics-driven method is still good. But the one different thing that we can see the vertical resolution between these 2 methods. Physics-driven method has a better vertical resolution than the data-driven method here. So here's one representative traces. It's traces 300 and in different 5 scenarios here using phase-driven method. We can see there's no big improvement well, from 1 well to 20 wells because we already have a good result with only 1 well here. But it's different in data-driven method. We can see there's a big improvement from 1 well to 20 wells because I think for this data, for this line, for the data-driven method, we need at least 20 wells to get a good result. So to test the performance in noise environment here, we add some random noise and then the seismic data is 10 dB signal to noise ratio here, and it's also the same true impedance here. We'll see the performance on this two different methods. We can see for one well, the data-driven method is terrible. There's a lot of chaos there. It's not even close to the, the color is not even close to right. But we can see physics-driven, the overall result is better, is close to the true impedance. But we can still see some discontinuity here because the noise, random noise. And then we increase to 3 wells, there's a better performance in data-driven method, also the physics-driven methods. And keep increase to 5, we can see the results become better and better, and 10 wells, and to the final 20 wells. We can see for data-driven method, it needs at least 20 wells, no matter it's noise-free or 10 dB noise contaminated data. And for these two methods, physics-driven and data-driven, data-driven has a better performance when in noise data when it has enough well numbers, like about 20. And here's the performance in the trace 300. We can see just a small improvement, while in physics-driven method, if we increase 1 well to 20 wells. But it's still the same for the data-driven methods. It can't get a good result with limited wells, 1 or 3, even 5. But it gets a good result with 20 wells here. So here we got two conclusions. First, physics-driven methods can produce high accuracy seismic impedance while compared with data-driven, and it's less dependent on the number of wells. And if the signal-to-noise ratio of seismic data is high, so it's quite sensitive to the noise because it majorly is rely on the difference between seismic data and synthetic data. If we can't get a clear enough seismic data, the result can't be good. And for the data-driven method, it's superior to the phase-driven method in predicting impedance for noisy seismic data. And if the number of wells reach a certain number. For this case, for this line, which has 512 traces, it needs at least 20 wells to do this job. So thank you. I'm happy to answer any questions.